Okay, yeah. Thank you very much. And also, I'd like to thank the organizers for inviting me and giving me the opportunity to talk about my research on open quantum many-body systems. And also apologies for holding you hostage for another 20 minutes before lunch. So what I'm going to talk about today is about driven-dissipative Rydberg systems. So what does this mean? I probably don't have to mention to you that Rydberg atoms are inherently metastable, and kind of the cartoon picture that we can take is that we assume, well, we have maybe a ground state, then we do some laser excitation to a Rydberg state, and this Rydberg state can decay back to the ground state. Of course, reality is much more complicated, but that is like the kind of simple minimal model that you can think of. And the nice thing about Rydberg atoms is that you have so many states available that you can essentially have a very high tunability of your interaction parameters and also the dissipation that you have in your system simply by choosing your Rydberg state you work with. And so you have strong tunable interactions and dissipation at the same time, and there can be interesting competition between the two effects. And how we describe this system, so we describe this in terms of a master equation. So this is a Markovian master equation in Lindblad form in our case. So you have the time derivative of the density operator, so it's the state of the system. The first part is equivalent to the Schrödinger equation, that's unitary dynamics. And on top of that, we get additional effects coming from the dissipation, which involve these potentially non-Hermitian jump operators. All right, and I mean, we like, as many-body theorists, we like to play with toy models, and so the simplest toy models that you can come up with is you look at the nearest neighbor Ising interaction on a lattice. So you have some what we call in the language of Ising model, you have a transverse field, so that is related to the driving strength of your laser. You have a longitudinal field that is coming from the detuning and also some part of the interaction, and then you have an Ising interaction between here, in this case, nearest neighbors on a lattice. And you have the dissipation, as I said. I mean, the kind of cartoon pictures that we have is just the first. I mean, just the Rydberg state decays back into the ground state. And if you do that, then I mean, there are also experiments that have looked at driven-dissipative Rydberg systems. So this is a plot from a paper by the group of Oliver Morsch in Pisa. And if you do some what I will show later on, variational calculations, I mean, we find it, I mean, pretty much even on a quantitative level, without having any adjustable parameters, you find pretty much the same thing. And then you are very happy and say, okay, this works in a great way. And so we can use these minimal models to some extent, at least to explain what is going on in these systems. But then you sit back for a moment and think, I mean, oh, why on earth does this even work? I mean, there you think about many things why that could fail. Yeah, I mean, if you have a nearest neighbor model, that for sure ignores the Rydberg blockade in the system, that we have already heard a lot of during previous talks in this workshop. But the nice thing is that basically the blockade also kind of cures some of the defects of these minimal models by implementing something like an artificial lattice. Of course, it's not a perfectly ordered lattice, but it has some structure that you can work with. But if you want to go to actual lattices, there's another complication coming into play. If you have a very dense system, so it's highly blockaded, you don't really care about whether you lose an atom from time to time, because maybe it decays into a wrong hyperfine state and then can no longer be excited or whatever can happen. So in these dense systems, you don't care about this. But if you put things on a lattice where you have like a single atom per lattice site, starting from like a mod insulator, then you would definitely care if you start to lose some of your constituents of your system. And I mean, and something that Igor has recently pointed out is also that if you go to a lattice system, there are additional complications that can come into play, that outgoing photons can carry information about the local environment, because they basically, the color of the photon encodes whether you have some interactions to neighboring Rydberg atoms in your system. So we kind of came up with a solution, at least to the last problem, by doing something that also several people already do experimentally. You add an additional intermediate state. Yeah, so here this is a 5p 3/2 excited state. This is not a Rydberg state, but you can couple this to an S state just by an additional laser field. And if you set your conditions right, I mean, then you have to solve out all these kind of effective jump operators. You integrate out this state here because it decays very, very fast. And what you find is that in a certain regime, so when this detuning here is much larger than your interaction in your lattice, then you can get something like an effective local decay rate, and then you have, at least from the viewpoint of these jump operators, you have something that corresponds to what you have in the toy model. All right, so that is like the structure why we want to I mean, start out looking at these dissipative Rydberg systems in more detail, put them on a lattice and see what is really going on to get a better understanding, I mean, where these toy models work and where they fail. And this brings me to the, I would say, main part. So I talk about the dissipative version of the Rydberg blockade. And then later on, I talk about some long-range correlations in critical systems and also a way to tackle this. So first of all, I want to point out, I mean, that the problems that we are facing there are very hard. Yeah? I mean, as any many-body problem, I mean, you have if you want to solve this exactly on a computer, you will face an exponential growth of the Hilbert space, which of course is very bad. I mean, you run into a wall very quickly. I mean, with these open systems, it's even worse because, I mean, you have the statistical notion of the state of your system. So even if you do some clever tricks like Monte Carlo sampling techniques, I mean, you can maybe do about 20, maybe a bit more of just two-level systems on a classical computer. So this is something that is clearly a problem. And one additional challenge is that many of the very successful methods that have been developed for analyzing equilibrium quantum many-body systems, I mean, for instance, quantum Monte Carlo methods, that is something that is not available for open systems because the rules of the game are very different there because we don't have any thermodynamic quantities, at least to begin with. I mean, we will come to maybe some ideas where how one is going to do it later on. So there have been previous attempts in tackling the problem. So one is based on a variational principle. This I will focus a bit more about. There are also other works involving, for instance, tensor network methods. So that's also something that we have already heard quite a bit about in this workshop in other contexts. And something that people have also done is using cluster mean field theory. So you basically, I mean, make small or partition your system into small batches, which you solve exactly, and then you stitch these batches together in a mean field theory or mean field decoupling, and you make these batches bigger and bigger, and then look how things scale. And if you're interested in all the details of these methods, we recently wrote a review article where you can find all about that. All right, so let me then come to the idea of using a variational principle to tackle these systems. So we are interested in the steady state of such a master equation, and that is, as I said, an exponentially hard problem. So what can we do? We can probably not hope to solve it exactly, but maybe what we can do is we can make a kind of a variational guess for the steady state and see how close we can get to the zero for the time derivative of our state, which would be the steady state. And so you send this to zero. This you can write as a kind of a big matrix norm, and then you have to play a few more games to actually get something that is computable. But there you have to be careful that you get something which is essentially unbiased. So there's a low battery warning. And so you have there are different norms that you can use. Yeah, it's not really important which one you take, but you have to be careful. And one thing is, yeah, you can, as the easiest variational manifold, you can use product states, and yeah, so you just have basically products of your single site density matrices. Yeah, so this R operator just makes many copies of that, and yeah, so if you look at the derivative, I mean, but you see time derivative with basically two effects. One is some purely local dynamics, so that is what you also have in kind of mean field solutions. But there is an additional term coming up involving the derivative of the correlation. So that's actually important to capture some of the effects. So now what we also want to include here, so we want to describe something like a Rydberg blockade on a lattice. So we have to also include like long-range interactions and long-range correlations. So we, have to decompose this Levelian. This is the generator of the dynamics. It's many terms, and you do this as a vectorized density matrix, and you get lots of terms, and so you have to figure out basically a way how to group them all together and calculate them. It's a bit of work, but it can be done. And then of course you have the question, what to put as a guess for your variational ansatz. In general, we want to do an ansatz which involves not just the product state, but something that also encodes correlation, which is, kind of good on the level of density matrices, because we can just add it to the product state solution in terms of these correlators. And for the correlators, what we use, in particular, the interesting thing is the pair correlation function between the Rydberg atoms. And for this, we make an ansatz for the Rydberg blockade. So you have here in total 1, 2, 3, and there's this in this R tilde, there's another parameter hiding. So we have a pair correlation function which just has 4 parameters, and the ansatz is chosen in a way that the limits that that should come out correctly. So in the weak or in small r limit, this goes like r to the 6. So this is basically at 0 you have 0 distance, you have perfect blockade, and then this goes down like 1 over r to the 6, or that goes up like r to the 6 as a consequence of the van der Waals interaction. And in the long range or in the large distance limit, it should eventually become uncorrelated, but there is a decay which is also going like r to the 6. So that is basically also what is coming from the van der Waals interaction. And if you basically put this all in and put it on, solve it for the steady state, and you see very similar things that happen also for these toy models. So they have some validity. So basically what you have here, initially you don't have any Rydberg excitations, and then at some point you drive the system hard enough that you open the floodgates and you get a lot of Rydberg excitations in the system. So this is also like a facilitation transition that what Igor just mentioned. So initially the system is blockaded, and then at some point, you get a phase transition to something where there's facilitation happening. And you can also look at this now from the pair correlation function. And this is what we can now have access to, because this is part of our variational ansatz. And you see that in basically below the transition, so the solid lines are below the transition, you get something which resembles like the standard Rydberg pair correlation function that you, for instance, also find in ground state, many-body ground state calculations. And this has this like standard blockade profile. However, when you go above the transition, what we find is that basically this becomes uncorrelated. So the interpretation is a bit different than in the short range model. There you would say, this is more this low density region behaves more like a gas. It's more like low density gas, whereas this facilitation rate regime is more like a liquid, because it's essentially incompressible. And here the situation is a bit flipped. Here you have some pair correlation function which looks more like that of a liquid, and here that one looks more like a gas. So using these toy models to find out the map out the phase diagram, that works more or less reasonably well. But the interpretation of the phases that actually appear is quite different if you have this long range blockade or not. All right. So how much time do you have?
Not very much. It 16 minutes already.
Okay. So then I give a quick over this. So so far what I've shown you is basically what we just had is essentially a first order transition in steady state. You can also have continuous transitions, and we have found ways to basically analyze that. Essentially, the idea is to use the variational norm as a concept at the free energy, and then you can play exactly the same games. Like you can make dissipative versions of Landau theory, so you can find all sorts of fancy things there. What we can also do now is not just go to the steady state, but also look at the way the system relaxes to the steady state. So you can come up with effective Langevin dynamics that basically describe how you approach to the steady state. But yeah, ask me about that if you're interested in it. So what I want to focus and briefly touch on the last part. So basically what I've explained to you now is, of course, something that works very well for these blockaded systems, but it's also something which is quite complicated to use. And something that we found out when you don't have these like long range interactions in the system, what works very well is the discrete truncated Wigner approximation. So the idea is to use some phase-based sampling to represent your quantum state. And so this could do it in the exact way. This is by using a Wigner function. And the idea is that you do this truncated Wigner approximation, that you basically replace these phase point operators. I mean, here that is still exact. You replace that by essentially classical trajectories, and all that is encoded, all which is quantum, is that it remains is encoded in your initial state. Yeah. So you can also do this now for spin systems. Yeah. So this was pioneered by Johannes Schachenmeier and Anna Maria Ray a few years ago. So one way you can think about this is you start with like spin polarized, say here in the x direction, and then the quantumness is encoded in that you choose random variables for sy and sz randomly between +1 and -1. So that's basically how that works. We also now made this usable in open quantum systems by essentially building a quantum jump method on top of that. So let me just skip that. So yeah, we benchmark this against something simple as simple two-level systems undergoing resonance fluorescence. So you see that you perfectly recover the exact solution. And you can also now adapt this to these short-range interacting toy models. Yeah, so that works also very well. And let me just show you this slide. And now we basically follow this jump and these short-range models. Now where we have this first-order jump, here you can follow this basically until you get to a critical point, and it's quite similar as like the liquid-gas transition in equilibrium systems. And if you follow that, and basically then you look at some finite size scaling theory close to this critical point. And although what we did essentially in this truncated Wigner sampling is we do a mean field decoupling of the interaction, you see that the critical exponents that you can extract here, they are actually coming out beyond mean field. And that is because what we are capturing correctly here is classical fluctuation. The only thing that we throw out is quantum fluctuation. So as long as you have a phase transition that is driven by classical fluctuations and not by quantum fluctations, these discrete truncated Wigner samplings can be expected to work extremely well. So that's my summary. So I just don't want to use any time. So we know that quantum systems are very challenging to deal with, but what we have now done is essentially capturing steady state phase transitions, which are driven by classical fluctuations. And of course, the next thing that we want to do is also looking into quantum fluctuations. Thank you for your attention.
Well, thank you very much for this very nice theoretical presentation. Yeah, question, please.
So you mentioned that you can use your variational approach not only for the steady states, but also the approach to the steady state. I mean, what's the limitation there? Can you do general non-equilibrium dynamics variationally, or like what has to be set? Like how close do you have to keep the steady state for this to be?
Well, this is so what you get here is there is some kind of mesoscopic time scale appearing. Yeah. So basically, you get some. This effective Langevin equation. They appear on some. They are valid on the time scale on this mesoscopic time scale. Yeah, but basically there is no kind of guarantee that this mesoscopic time scale is reached after whatever time you want to look at. It could be that, of course, if you want to look at some initial dynamics in your system. That you're outside of this window where this mesoscopic time scale appears. Yeah. So then
wait for that to appear.
yeah. So basically, this is so to say you can understand this as basically the last bit of a relaxation towards the steady state. Yeah? So this is basically where all this but this is where when you want to look at things like I mean breaking detailed balance and things like that, this is already something that you see on this level.
So phase transitions we cannot do that.
I mean phase transitions in the sense, I mean usually when we talk about these phase transitions, we talk about thermodynamic limit and long time limit. So this is clearly in the long time. I mean, this is basically how you approach the long time limit. So in that sense, it works. So you can, but it doesn't really, I mean, tell you when this mesoscopic time scale is reached. Yeah? I mean, what numbers you have to associate with that. Yeah.
The question by Igor.
Yeah, just maybe I didn't quite fully get the picture. So on one side you said you find only this first order transition. Is this correct? In this last work you did, and then there was an earlier work where you did some scaling, which was very continuous.
Yeah, I mean, okay, that depends on what. Yeah, I mean,
but I mean, what you do is standard work, open system.
Yeah, I mean, we actually okay. So actually, what you can, I mean, here this is a first order transition, but there's also a way to make this continuous. For instance, the simplest way is actually to put the dephasing into the system. So I mean, you also looked at this on the mean field level, right? And then you also saw that.
You know, but I would even think that the topology of the phase diagram would be weird if this first order line wouldn't end somewhere in the second order transition. And we have another X, right? You know, you have 4 parameters to the system.
Yeah.
Gamma, theta, omega.
Yeah.
One you can kill.
Yeah.
So I'm not saying I bet my house.
Yeah.
So I'm rather confident that there must be a way to make this nice and germinated.
Yeah. That's I mean, you can do it by tuning the interaction, or by adding dephasing to the problem. I mean, then you see that this basically this first order jump becomes smaller and smaller, and at some point it becomes critical. Yeah,
So I see no further questions. So before I hand in to Stephen for the last words, let's thank all the speakers of this morning.